Kiran, I cannot hear your voice. Can you hear you? Can you hear me? What about Sai? Are you okay? Can you hear me? Hmm. I'm not hearing their voices yet. Sai? They're there?
Yes, sir.
Yeah, Kiran, I think you can hear. Can you come on? Can you come on? Can you hear me? He can hear me, but he's not saying anything.
All is connected.
What is that? Yes, yes, you. You are there? Yes, sir. So, he's a soldier. Kiran, come on. Forward. Security, come on. Straight from you connected from me in this minute. Let me get connected. Oh, yeah. So about this. Yeah. We'll start the class in a couple of minutes. You got it. Yeah, we can decide on but sorry. Mohan Sikand. Can you hear me, Mohan Sikand? Yes, sir. Other people will come because the students are come. Students will not come because I'm going to revise this course. Okay. Correct. Yeah.
Good morning, sir.
Good morning, Mohan. You can hear my voice very well.
Yes, sir, I can hear very well.
Very good.
My volume was down, sir. That's why I could not respond properly.
Okay, so just one word to Kiran Kumar will also join next. What I have decided is that you guys suggest why. I thought I would discuss a little bit topology that went in already for your use. And one of the students actually is complex. We'll start complex in a couple of days. Okay, so you and Kiran Kumar will only be the students today. Okay. So anyway, Kiran is joining in a few minutes. First year, it will take some time to set up about them. So, have you been able to read a bit of topology?
Yes, sir.
Where you read topology stuff?
I'm acquainted with open and closed.
We'll start here in the beginning. I think Kiran will join soon. They will discuss with me, repeat whatever. We'll start with what is called metric spaces. Let's be economically set. Okay. Function D from x plus x are satisfying the following is parametric arrays. What are the conditions that I am expecting to see that D satisfied? D xy is greater than equal to 0 or x and y in x. Metric is the relevant distance for your 2 points. So if I take 2 points here and I want to find the distance between 2 points, that's the possible condition. Indeed, if the distance between the 2 points is 0, you insist the 2 points to be in the same place, right? And equality holds if and only if x equal to y. I write IFF to say it is if and only if x equal to y. So the distance between them is 0 only when both the points are the same place, right? And 2, there is a set of about of symmetry. Distance from x to y, here is x and here is y. X to y is same as distance from y to x. For all x and y in x. And finally, there is this triangle inequality. Instead of going x to y directly, you might go somewhere and then go to some other point z. Then x to z, z to y, that total distance is always more than equal to distance from x to y. So distance from xy, distance between x and y is less than equal to dxz plus dzy dxz plus dzy for all x, y, z in x. If these three properties are satisfied, I say this D is a metric on x. Okay. And then x comma D, this pair is called a metric space. Okay. So it's imitating your usual feeling about the distance between the 2 points. This is not the usual distance. Any something a function D which satisfies this kind of property is called a metric, and this is called a metric space. Okay, so we have back in of mind the usual Euclidean plane and the distance between 2 points. This is what you have in the back of your mind. As an example, I can take the usual x to be the usual real line, r, and the distance between x and y is defined to be, and for x and y in r, define dxy is just the modulus of x minus y. You will notice that mod x minus y satisfies all this condition. Mod x minus y being an absolute value, mod x minus y is non-negative. How can that be zero? Only when x equal to y. The first condition is satisfied. Mod x minus y or mod y minus x is the same thing. Second condition is satisfied. And third condition is also easy to see. So this is a metric on R. Okay. This is D is a metric on R. Okay. I can have the same kind of a metric on a complex plane also. In complex plane, C is the set of all complex numbers. You have the absolute value mod z of any complex number. If z is x plus iy, mod z equal to root over x squared plus y squared, that actually gives you distance. So there we define for z1 and z2 in R, define once again, define distance between z1 and z2 to be modulus of z1 minus z2. Okay, this also becomes D is a metric. It is a metric on R. I'm not going to give you too many examples right now. Right? So what is a metric space? How does it really operate? That's what I want. So that's also a metric. You can easily know complex numbers satisfy all these conditions. Mod Z1 minus Z2 is always non-negative. Equal to 0, only Z1 equal to Z2. Mod Z1 minus Z2 or Z2 minus Z1 modulus is the same. All these conditions will be satisfied as metric. What I want you to see from here is, I'm going to the next page. Are you okay? I will go back again. Okay, anything you want?
Understood, sir. Yes.
Yeah. In general, we have what is called Rn. X is Rn. Rn means antiples. Set of all antiples. X1, X2, and so on, Xn, where each Xk is a real number. Okay, that is the R class are n copies of it. And then any point is written as x bar for x bar, which is x1, x2, etc., xn, and y bar, y1, y2, etc., yn. Okay, we define dx bar y bar is equal to, I think, usual distance. So sigma xk minus yk whole squared, xk minus yk whole squared, k equal to 1 to n, always to the power 1 by n. This is the usual, the thing you write, right? In case of distance between 2 points in the plane, is x1 minus x2 whole squared plus y1 minus y2 whole squared under root. In in three-dimensional space, it is x1 minus x2 whole squared plus y1 minus y2 whole squared plus z1 minus z2 whole squared power 1 by 3. Sorry, whole square power half will be good enough too. There's no need of 1 by n. I take it back. Whole square, whole power half. That's good. Sorry, that's good enough. Take it back. This is also a metric. I'm not gonna pay it time, put any time to see why this is a metric. Okay, so D will be a metric. Right. Now, what I want to do is in a metric space, I have a way to measure a distance. So here is a point, and I can measure a certain distance of about R and put all the points which are within the distance of R. And I would like to call that from the center, right? If this is some X in that and this is R, all the points inside this, I would like to call that DXR, okay? So here is the notation we have for X in the metric space X. Okay, so I have taken XD in the metric space in all, but what happens? Let XD be a metric space. Okay, so it can be R with a modulus, or maybe complex plane with modulus, or maybe Rn with modulus, that thing defined. It doesn't matter, any one of them. Okay. We don't study abstract metric spaces really in our course. In this course in complex function theory, we are only interested in complex plane with the usual metric smart Z1 minus Z2 is the distance between Z1 and Z2. We'll be interested in only that. Just I'm saying it in general, but we restrict only to complex plane eventually. Suppose the metric for uh, X inside capital X and R greater than 0, the ball BXR consists of all the Y in the complex in the metric space X, whose distance from X to Y is less than R. That is this what you call open ball. Whereas you have the B bar XR will consist of all Y in X, such that DXY is less than or equal to R. Okay, this is the closure. Okay. What I want you to, right? Is it okay? That's how. In this case, I include in our common sense language the boundary too. This is actually without the boundary, everything inside. First one is everything inside, that's all, at a distance less than R. But this one is um, including the boundary. All the points on R are also taken. I could have introduced some more fancy metrics too. Then you will see that a ball will look out very strange. For example, if I give you a fancy metric, maybe another example. Okay, I'm adding here. Suppose I add another example here. Let's say X is uh, C, which is R cross R, R2, okay? And this X1, Y1 is one point, and X2, Y2 is another point in R cross R. I can define the distance between X1, Y1 and X2, Y2. The distance could be defined to be maybe, I think, maximum of. Hey, Kiran, welcome. You're there. Okay. Kiran, I didn't do too much really. You know, I didn't really do too much. I just tell you what I just did. I'm going to go to the previous things. All I said is introduce what is called a metric space. Okay. Metric is a mapping from X class X to R, so that I take an input as X and Y, an ordered pair, and find out the output is a real number, assuming that dxy is non-negative for all X and Y in X, which is what the usual distance between 2 points will do. given any 2 points, we know what the distance between the 2 points in the usual plane is. The same ideas have to come here. So distance between 2 points will never be negative, and it will be 0 only when the 2 points are at the same place. And the distance from x to y and distance from y to x are both equal. And one more last thing is this triangle inequality. So going x to y straight, you can go to some z and go there. Then you increase the distance, right? That means the distance from x to y is less than the distance from x to z plus z to y. If these three properties are satisfied, it's called metric. Okay, and the usual metrics we are familiar with is in the real line mod x minus y, in the complex plane mod z1 minus z2. Okay, sorry. Okay. And then I have started defining for any point in the metric space. I said if I fix a point, I look at all the elements in the metric space which are nearer to x by r is the open palm that consists of all the y whose distance from x is less than r. Whereas if I allow the distance all the way equal to r, I'm actually allowing the boundary also come into picture. So in this case, it is not only the ball, including the boundary. The boundary is also including all the way to the boundary. If you include all that, that's a closed ball. Okay, right? Okay. Yeah, that's it. Hmm? Yeah, I was trying to give you a fancy metric. That's okay. Just leave it. We will have an idea. Next, please.
Will it give a
Now,
square?
yes, please.
That fancy metric you just erased, will it give a square? The ball, does it take the shape of a
Yeah,
square?
yeah. It will give you a square. Okay. I'll show you. I will give you that. Let's talk about that metric. There's no need. Okay, I'll explain that metric. Okay. So one more metric I'm introducing is on R cross R, which consists of all the points x comma y, where x and y are both real numbers, and introduce the distance between a pair of points x1 y1 and x2 y2. I will not be interested in this metric later on, but just take this. This is I can say uh, distance between the two things is maybe minimum of distance between x1 and x2, comma y1, y2. I look at that. Okay. Now, for example, one point is 0, 0. Okay. And any point xy is x1, y1. Okay. What is the distance between 0 and x? Okay. That is actually minimum of mod x1, comma mod y1. Is that right? And if I want it to be less than r, either minimum is less than r means okay, maybe I put maximum. I'm just making up some problem. Maximum. Suppose maximum is less than r means one of them is the maximum, other is small. Okay. So my metric is maximum is that. So one of them is maximum is less than r means maybe maximum of the two is the first one, and that is less than r, and maximum is mod y, and that is less than r. So this is if and only if two things. Maximum is equal to r, and the other is less than or equal to r. Okay. Or maybe the maximum is this. So mod y and is r, and mod x1 is less than or equal to r. What does it really mean? If you really look at it in the real life, you are saying that if you really look at it in the real life, I'm saying is that if maximum is r, x coordinate is r, x coordinate is minus r or plus r. But then the y coordinate is between minus r and r. So this is minus r, this is plus r. But the y coordinate is between, so y coordinate will go from here to here. Okay. And right? Uh, y coordinate will go from here to here. But in this case, mod y is r. So whether y is plus r or y is minus r, then x coordinate is between minus r and r. There you go. So what happened here? This minimum is less than r means you're looking at all the points which are actually inside this. Oh, it is the boundary. Are you following that now? So I want it to be equal to r means that boundary. Less than r means you get all those squares. All of them will give you this. So this is the ball. This is the ball centered at 0 of radius r. If it is open ball, the boundary is left out. If it is closed ball, including the boundary. There you go. So this is a fancy metric which has given use. What is the metric for us? I define it to be maximum of mod x1 minus 1. So maximum. Okay. The back of my mind have balance like what I see in the case of the quantum plane, but does not look like that. It depends on the metric. Okay. But I'm not interested now. I'm interested in only with express. Sikha, did you get that?
Yes, sir. Yes.
Less than 100. In case equality things to be equality means what? Suppose this is equal to. So equal to r means maximum is
Including the
equal to
boundary, closed ball.
Yes, equal to r means if this is the maximum, then that is small. So either mod x is r or mod y is less than r. R means this is the maximum, that is r, but that thing is less than r. Okay. So in case this is r, x coordinate is minus r plus r, but y coordinate is between minus r and r. So x coordinate is minus r plus r, y coordinate is between minus r and r. So all the points are taken get, all the points are taken. And in this case, these points are taken. That is exactly when it is r. If it is less than r, it can be any s less than r. Then I can keep on getting all these things. So then I'll get all, this will fill the whole thing. So basically, this whole thing is going to be the ball without the boundary part. Okay? So you can have such examples. You can have one simple thing. You will have maybe something like this if I just appropriate. If I have all halves and things like that, maybe we get something like that.
Yes, sir. I think I raised it to the power of 2 by 3. We'll get such a twinkle twinkle.
Yes, exactly. You got it? So next. What I want to see is the definition to begin a subset G of X. Actually, what I'm doing is I'm just quickly, so that is not there. So I'm just quickly revising a few things on top of the okay. That's what I'm doing. A subset G of X is called open. We actually need to find this way. Let's see. Definition of a interior point. Let G be a subset of X. Okay. Point with an element X and G is called the interior point. G. If find this interior point, if somehow a small ball in G is completely immersed inside G, if there exists a R greater than 0, such that the ball central of X and radius R is contained in G. So it's an interior point. Okay, that makes sense. And if we take a region like this, if I take any point here, because all this is the set G. If I take a point here, no matter what circle you draw, part of it will go out. That's not going to be the point. I want to say it's a boundary point. Okay? Right? So when there's a point like this, I would be able to draw a small enough distance over that, which is completely contained in G. Even if the point is very close to that, I just be careful to draw a very small thing. So as long as you can get a small organ, then there is something extra. Extra radius R is okay, and a set G is said to be open. A set G in X is said to be open if every point of it is an interior point of it. Is said to be open if every point of it is an interior point.
Sir, is that ball the same as neighborhood?
Yeah, really. It's an area. It's an arm neighborhood. Okay, it's an interior point. You're right. That's how we define it in neighborhood. Immediately you notice that indeed G is open if and only if G is a union of several balls. Okay, if and only if there exists any, okay, if and only if there exists G is union of X or non-independent X, where X is in some index set. What I want to say is that, that's why happens. If set has to be open, for each point in the neighborhood, there's a neighborhood. Union of all these neighborhoods should also be completely sitting inside G. So G is open if G is several, maybe not very something in total maybe parts. G is open if G is linear of open bars. Of open bars. A collection of union of a collection of open bars. Can you see that? Every point they will find very close to each other. Every point, so when you take the collection of all these intervals here, they really be continuing the point G. Already there, and that union is contained in G, because every ball is contained in G. And what you notice here is a little theorem you can see, very easy. Is in a metric space X2, the collection of open sets satisfies the following property. The collection of all open sets, okay, collection of all open sets X satisfies the following property. Okay. One, LP set in the whole space LP set is open because there's no point. There's no point, it's not an integral point. Okay? Because there's no point now. It's open when any point of it is an integral point. So the accuracy, simplicity, full space, okay, are open sets. So if G alpha, alpha and delta are all open X, then union G alpha, alpha and delta is also X. Yeah. So what happens is, somebody have a lot of open sets, inter-open set, inter-open set, inter-open set. If we take any point in this, why is this an interior point? This is in a G, so the little bar which is contained in that. So that's an interior point. Why is this an interior point for two reasons? And the interior point of this is interior point of this. So in that sense, this will be every point of it is open here. How do I say this open? Every point of it is an interior point. Delta is only indexation. G1, G2, G3, I can say maybe. Okay, so that's right. Delta may contain multiple meaning. If it's uncountable meaning, it contains many things. For every index alpha and beta, then the opposite alpha. Then their union is why this European church you have to every point of it is an interior. So take a point in. I took a point in the union, and the point in one of them. If there is a point in one of them, that one of them is open set. It is a point inside them. That's how the Indian point of this little ball, which is contained in GR. If this ball is contained in GR, it's contained in the entire unit. So that point is an interior point. That's right. And three, if the G comma H are open in X, then C intersection H is open in X2. Okay, that's also clear. If I have a open set here and I have an open set here, corresponding to this point, there's an interior point of the first set, and therefore there's a path sentence coming. It's an interior point of the second one, so the little path that is just going to stay inside that. And then out of the two balls, whichever the smaller ball is, that smaller ball will lie both of them. So that point is interior to the intersection. Okay. Right. Okay.
Yes, sir.
So that way, it's all built in intersection also. This is actually when these three properties are satisfied for any collection selects, the works of X is what topology. A topology and an abstract set X is nothing but a collection of sets which has the following properties. And if it's a collection, and if I hold a lot of sets in that topology, then the union is there. So it's an arbitrary union, whereas it comes to intersection, it's not variables. Whereas the two things intersection should be that, therefore, effectively, it's for two things for quantumly very can only be. So if you want to replace this last one as follows, you can replace the last one as follows. That's better too. If G1, G2, etc., Gn are open, then then intersection Gk, k equal to 1 to n is open. Okay. So arbitrary unions and final intersections. Indeed, that's what the topology will be, and justify that from the response. Any questions so far?
Yes, a small doubt regarding the union of open sets.
Hmm.
So we thought that if G is open, G can be represented as a union of infinite open sets.
Any number. Yeah.
Yeah. So if we represent it as infinite open sets, somehow the limit of the union can be a closed set, right, sir? Limit, not the actual union, but the limit.
No, it is not. That's what the character says. Open. Okay. I'll tell you.
Okay.
I will prove this second one. Okay. So proof in the second. Yes, of course. Okay. What do you have to show? In order to show that union G alpha, alpha and delta is open, this is what I want to show. Right question. Means I should show that every element is continuous. So take an element X in union G alpha, alpha and delta. I want to show something. This is in any G alpha means it's in one of the members. This implies there exists one alpha in delta such that X is in G alpha is open. So there exists R greater than 0. There is X is an interior, therefore X is an interior point of here. That means there exists an R greater than 0, such that BXR is contained in every topology. There exists a alpha, there exists an alpha naught. Specific thing, right? Okay. So there is a G alpha naught. But G alpha naught is contained in the union of all G alpha. Alpha, yes. Alpha naught is one of them. So therefore, I can put a ball around that X, which is contained in the union 2. So this union is open. So I showed you that every point of this G contains a ball around X. It has. Now, the Q project is also open. But what? I don't think arbitrary union of open sets will be closed. No, that's what you're saying. The property I have derived is arbitrary unions of open sets is open. And finite intersection of open sets is open. But arbitrary intersection of open sets, I did not prove it is open. Actually, arbitrary intersection of open sets, I don't know what it is. Okay?
Yes, sir. I was just keeping in mind that sometimes limit of a sequence cannot be a term of the sequence, right, sir? So I thought the limit is not actually the union. If it just covers the rest of the points, it can be closed. That's
It doesn't. In this case, the open bars, when you put
yes,
all open bars together,
yes,
still stay together.
still open.
But
Yes.
intersection will be. I think I've shown what you said is very nice. For example, uh, with the intersection, if I look at an R, I'll say what you said. You read it very, very well. If I look at minus 1 by n to 1 plus 1 by n is your GN. It's the interval like this here become 0 and become 1. I just gone slightly out to this left, slightly out to the right, and I've taken this open. Okay. Now, if you look at intersection GN, n equal to 1 to infinity, you can show that this becomes 0 to 1. Closing to 0. This will be closer to 0. That will be see, arbitrary intersection of open sets. I am not required. I cannot prove it. So actually, it doesn't have to be. Okay. This is actually the close. It's complement of it. This is the complement of minus infinity to 0 union 1 to infinity. There's an open set, and its complement is that, and so is it. Okay.
Yes.
So the upshot of all this discussion is the following: the definition of the topology. Okay, let X be any planet set. The collection of subsets of function T, subsets of X is called the topology of X. If one empty set on the whole space, 150, two is close into empty unions. Okay? For any connection, G alpha in delta of sets in T of sets in T, the union G alpha in delta also belongs to T. And find the intersections. And if G1, G2, the Gn belong to T, then the intersection J, N also. So if these three properties are satisfied, this function is logic topology. Next. So what we have done is, in case we have a metric space, produced a topology on the metric space by defining the set G to work with the empiric point of the interior point by interior point again, the interior point if by making a literal bond, the matter is small. And so we can find the number of the bond is in J. But every point in J is a bond like that, point inside J. Then the point in J interior point, and then G is open. So collection of open sets in a metric space is a topology. That's the collection of all open sets in a metric space. This definition doesn't require external metric space. These are very general topological spaces. When we study topology, we study in general. The set the collection satisfying all these things. Okay? Is what is the topology? If T is a topology on X, we call X the pair X comma T in a topological space. We are not interested in topologies right now. Okay, I'm only interested in one kind of topology coming from the document. But topology is a subject that analysis part but also another course complex numbers that we can study this. So not very complicated, very nice topological spaces, topologies are available. Studying them is an abstract. We don't want to do that in our course. What we want in complex numbers is the following. So we have noticed that if XD is a metric space, the collection of all open sets, the collection of all open sets. Next is a topology next. Topology on X. That is the topology we want. Actually, to be truthful, I don't even want to study. That's called a metric topology. Okay, topology induced by the metric. Okay, that topology is called the topology Rx induced by T. That topology is called the topology Rx. Induced by D. You already saw a very strange kind of sense to be if you allow your different to be very strange. Okay. Anyway, I'm not interested in all that. I'm only interested in the complex field together with the topology D, which is given as D, Z1, Z2, this is more Z1, Z2. In the complex analysis course, I'm only going to study this, nothing else. Okay? A set is said to be closed if its complement is open. A set A, F is simple. F is said to be closed. So everywhere it's only about metric space. XD is a metric space. To be specific, maybe CD is a metric space. It's only about those things we're talking. We're not talking abstract spaces. Okay? A set F is said to be closed in X. If its complement X minus F, this is the notation of the complement. All the elements. X. Okay. Sorry. Okay. Set F in X is said to be closed if X minus F consists of all the elements X to the set X, which are outside F, is open. Okay. So this is what it is. You have a set, right? They are closed sets. And for closed sets, you can see because the complements of open sets, you have a very similar easy result. If you look at arbitrary intersection of closed sets is closed, and a finite union of closed sets is closed, empty set and the whole space are closed. Okay, so note empty set and X are closed to if F alpha, alpha and delta is a collection of closed sets of closed sets, then their intersection F alpha, alpha and delta is closed. Okay, whereas only finite union of closed sets is closed. If F1, F2, etc., Fn are closed, then only the finite intersection, finite union, F R equal to 1 to N is closed. Okay. You see that? Why arbitrary intersection is closed? Because arbitrary intersections complement and arbitrary intersections, if you want to say it is closed, you want to show its complement is open. But the complement is union F alpha complement alpha and delta. Okay. This is the De Morgan's law. Complement of the intersection is union of the complements. But each F alpha is closed, so F alpha complement is open, and it's an arbitrary union of open sets is open. So that's why it's an open set. Therefore, this alone is closed because the complement is open. This alone is closed. So that's what it is. Now, a couple of very simple things. Given any set, A, we have interior of A, we have closure of A. Okay. Closure of A is denoted by, please, this is the notation for closure in topology. A bar. In set theory, usually A bar means complement of A. It is not that. It is A bar in topology is denoting the closure of A. closure of A is what? All the closure sets that contain A, I look at their intersection. Okay, it is the intersection of all closure sets containing A. F is closed and F contains A. So I'm approximating the J from above. But arbitrary intersection of closed sets is closed. So this is closed set. So A bar is a closed set containing A. Okay? Interior of A is you look at the open sets inside A and take their union. This is union of all G. Okay? G is contained in A and G is open. G is open and G is contained. See that? Whatever content I can have inside open sets, inside A, their union is A. But now arbitrary union of open sets is open set, so interior A is open. A bar is okay. A bar is not only closed, it's intersection of all closed sets that contains A. So I think in some sense, this is the smallest closed set containing A. This is the largest open set contained inside A. So it is largest open set contained in A. Contained in A. This is smallest closure set containing A. Containing A. Got it? Okay. Actually, what I put in that file, I did several days where I tried to understand what is the structure of this A bar or interior. Essentially, A bar is like A is there. If you can introduce convergence in the topology and so on, if in the metric space you can introduce convergence. If A is there, okay, if A is there, closure is going to be apart from all the points of A, they are the sequential limits. All the sequential limits you have to any sequence converges to here, all those sequential limits have to be attached to A to get the closure of A. So a point will be in A bar only when I can see that it is a limit of points inside A. The point is in A bar. So I want you to just read the introductory part in that book, as I told you, right? In the particular chapter. Excuse me. I have already done in the course. Excuse me.
Conway, sir?
Yeah, from Conway. First one is chapter 2, metric space topology. I've done that. So I'm only discussing part of those things. So you can just read it yourself once very quickly. Okay. This is done. Okay. Next. I have three properties I have to discuss. Three ideas. One is connectedness. One is connectedness. And there is compactness. And some more ideas. So connectedness and compactness is what I want to talk. First, the connectedness. Okay. Basically, this is the story. If a topological space is union of two disjoint open sets, this is an open set, this is an open set. and they're disjoint. Then the topological space is only this one. X is T union H, where that is open, this is open, and further their intersection is empty. And each is non-empty. G is non-empty, H is non-empty. So if I can split the topological space as union of two disjoint open sets, I say the topological space disconnect. Okay, right? A metric space or a topological space, a metric space, a topological space is said to be disconnected if there exists if X can be written as if X the topological space X is said to be disconnected if X can be written as union of two disjoint non-empty open sets. Disjoint, their intersection, disjoint non-empty open sets. Okay? Huh? If you can write it as disjoint union of two non-empty open sets, the space is disconnected. So space is connected when you cannot express it as union of disjoint non-empty open sets. If somebody says J and H are open sets and their union is X, if X is connected, either G or H has to be empty. You cannot have two disjoint non-empty open sets unite in X if you want the space to be connected. So disconnected means this. Okay? You will have to notice that in case of R, okay, in R, these are the two results I did. Okay, you can see which sort of matches with our common sense idea in the usual plane. I'm not proving them, which is the following. So here is one theorem I prove. R with the usual metric. Okay, this is what is called a usual topology. In that, okay, in that metric space, RD, okay, that is the usual topology on R. A set is connected. A set is connected. A set in R, okay, set in R is connected. There may be many topologies. We are only interested in that particular topology only. That is induced by the usual metric. Is connected if and only if it is an interval. If it is an interval. Okay, only intervals are connected. In the real line, if you really look at this open set union, this open set, clearly there is disconnected. They're disjoint and they're non-empty. Okay, and you cannot have any. I think you understand that. If you want a set to be connected in R, it has to be interval. Okay, whereas in C, the following happens. A subset. This was a little, work to be done. I don't want to repeat all that. The proofs are there. I have presented every year. Maybe we can get you the videos too. Or you can read the book. All this discussion connectedness is there. A subset, subset A of T is connected. If and only if, okay, if you want in the complex plane, set is connected. If and only if given any 2 points in it, we should be able to get a path joining line segments like this joining this point to that point. That's the only way it's going. Okay, so you should be able to reach out any place you want from any place you need in going in polygonal paths like that. If not, if for Z1 and Z2, maybe for Z and W in A, there exists a polygonal path. I call that Z2, Z baby Z1 to Z2, Z3, etc. Zn minus 1, Zn equal to W in that set A. I think I just write it in words. Okay, so what you mean that, in this diagram too, what I mean is that, suppose this I is connected Y, because if I take a Z1 here and I take a W here, I can put a path going like that. Okay? Then only that will be connected. Otherwise, it will be disconnected. We proved it in the class. So we want to talk about connected sets in very repeatedly in complex function theory. And you don't have to worry too much about it. At least you have to bare minimum recognize this particular idea. A connectedness actually in complex plane will actually come down to the following. In an abstract metric space, it doesn't work. In complex plane, it works. Okay. If this space is connected, any 2 points can be path connected. They cannot be connected by a path. Okay. All I need is that much only from that course in that. It's about connectedness. Okay. Then I have done. Is that okay, sir?
Yes, sir. Yes.
I've taken some time to prove all these things, but don't worry about it. Let's not get into all these things now. I'm just quickly going. Then I have talked about a very important idea of completeness, connectedness, completeness, and compactness. Next is completeness. Okay. Completeness is the following. In a sense, this concept we introduced, in some sense, does not allow any holes in the space. That's what actually completeness gives you. If you really look at in the rational numbers, set of all rational numbers, which is inside R, how this is a little unfortunate thing that if you look at sequences of rational numbers and their limits can become irrational numbers. Okay. So you have sequences inside Q, which might be accruing onto each other, but they converge not in Q but outside. You don't want that. Whereas R will be complete. No matter what sequence you take, if it converges to an element in R only. Okay, this is what I want to say. Okay, to come to completeness, we talk about what is convergence and so on. Okay, let Xn be a sequence in X. We say Xn we say Xn converges to an X, or we say Xn converges in X if there exists an X in X and a distance between Xn to X tends to 0 as n tends to infinity. Okay? Okay? Actually, we say Xn converges to X. We say Xn converges to X as n tends to infinity. Okay? In other words, in epsilon delta argument, you can say that that is for every epsilon greater than 0, there is a large enough n, a natural number, okay, or a positive integer, such that the distance between Xn to X comes very close to it. So the distance between X and X should diminish and should tend to 0. So it can be made smaller than epsilon for all n to the. Okay. Now we also introduced what is called a Cauchy sequence. A sequence xn in X is said to be Cauchy if in some sense xn and xm come close to each other. If for every epsilon greater than 0, there exists a large enough n, a positive integer, such that distance between xn and xm will be less than epsilon for all n and m greater than equal to n. So what sort of a sequence is that? If you wait long enough beyond a capital N, if you take any small n and m beyond that, the two elements xn and xm come too close to each other. So they are like coming on to each other. That's when you say the sequence is Cauchy. Okay. You want them to come even closer than epsilon, you can do it. So for every epsilon greater than 0, you can have epsilon to be 1 by 100 or 1 by 1 million. Who cares? You can make epsilon as far as you want. Still, I will be able to achieve this thing. The distance between x and xm is less than epsilon for all million. That's when you say Cauchy. For example, in the case of rational numbers, you get into these kinds of troubles. Let's say, you can have a bunch of easy sequences. Let's say 1 point root 2 is 1.414 something. Okay, root 2. 2 is 1.414. I forget the next digits. Maybe year 4, year 5, year 6. It's going to go forever. Non-terminating on the day. Now, if you look at the sequence, x1 equal to 1, x2 equal to 1.1, x2 equal to 1.3, x1 equal to 1, x2 equal to 1.4, x3 equal to 1.41, x4 equal to 1.414, x5 equal to 1.4, a4, and if you go on, sequences like that. Where are the terms? I have a sequence of numbers which converges to root. You see the sequence which is converging also becomes Cauchy. It is a Cauchy sequence which converges unfortunately not outside Q, but outside. So Q is, that's what I'm trying to get towards. So I tell you this. Here is a little note, okay? If a sequence converges, if xn converges, then it is Cauchy. Very easy to prove. Every convergence sequence is Cauchy. Because if xn converges to x, if xn converges to x, the distance will be the distance between xn and xm, x can be made very small, Now, if you mn the n and crossing n, then you will see the following. When n cross n, then you see the distance between xn and xm is less than the distance between xn and x plus distance between xn and xm. And this is less than epsilon, this is less than epsilon. So the total is less than epsilon plus epsilon is less than epsilon. So I can make this difference as far as I want. So originally start with epsilon by distance here, then this will be less than epsilon plus. So every convergence sequence is Cauchy. But Cauchy sequence is not converged. I can easily give you, because this sequence is Cauchy because it converges in R. But that doesn't converge in Q. So in Q, I have Cauchy sequences do not converge. I don't want, that's what completeness is. A space is said to be complete if every Cauchy sequence in that converges. Okay, but the converse is not true. Okay, the colors is that that's clear sequence. Okay, uh-huh. Okay. Root 2 is maybe 1 point A1, A2, A3, etc. forever. Okay. Then xk is equal to 1 point A1, A2, etc. in k. Okay. Xk converges to 2 in R, and therefore xk is Cauchy. You know, there is Gaussian. For Gaussianness only, they have to come close to each other. In R, in Q doesn't matter. It's Gaussian. In R, I don't want to say in R also, Gaussian. But Xn does not converge into Q. You got it? Okay, so there may be Cauchy sequences which are not converged. So here is the definition. Okay, the definition is a metric space X is said to be complete. Complete. If every Cauchy sequence is if every Cauchy sequence to be taken as a theorem is R is complete. Every Cauchy sequence in R converges, and even C is in the complex plane also. Take any sequence, definitely class. But Q itself has a space in which there was elements. Q is right. Okay. So I want to begin the first few sections in context. We have a compactness, assumption about significant compactness. Maybe we have to concentrate when talking about that. That's the definition. So Monday, on Monday proper, we continue with the connection. We know that this actually, there is something very special about complex social theory. We have to catch the point. Of course, we don't know the continuity, the differentiability. These are the kind of concepts we talk about in the complex theory. So, what is so special in complex analysis? We have studied the mathematical analysis and all. Why complex analysis is so big? I can talk about analysis in all. What is so special in this analysis of complex theory? When we see that, we do that integration one day. Slowly see why complex cancer. Actually, one of the properties that we see in books is that you can have a function differentiable R, but the derivative will not be differentiable. The derivative will not exist. But a complex thing, if a function is differentiable in a neighborhood of a point, is difference to one certain point, then it will be differential infinitely matrix. You don't have to verify the difference to this one. The function is differential in a small neighborhood in the complex plane. Then in that neighborhood, it's twice the difference. Whatever different differential. That's very important. It happens many times in partial test also. A function says it will certain amount of regularity. When it says it's a partial classification, you have a higher regularity that you make it normal. You don't have to verify that, it just comes out as a practice. As it is a solution to the when it is as a regular, it's a higher regularity function. Function, the related function also is the solution for a partial. That's how it's done. So whatever you learn, you can get excited about that. So the real and imaginary parts of construction are harmonic because they are the solutions of the partial motion question. Those who do existence, you would always. That's all. So there is very special about something. Let's make a name so that let's try to just start about that. And then that's all for me. Good stuff. If you have any comments, please go ahead. That's it. Then we'll stop. Thank you. Okay, fine.